A wealthy American investor is planning to build a mega mall in his rural area. He would like this mall to be just as large or larger than the biggest mega mall in America, so he hired 3 privately contracted systems engineers to minimize the cost of installing the optimal number of elevators and escalators in his new mall. The cost of installing an elevator is $110,400, and the cost of installing an escalator is $171,500. For Company 1, the customer must order at least 10 combined units of elevators and escalators as part of their shipping and packaging deal. For Company 2, the customer must order at least 15 combined units of elevators and escalators. The customer must also purchase at least 2 escalators as part of their shipping and packaging deal. Now, to solve this problem, we have to identify our decision variables and our objective coefficients for the optimal solution. Now, let's say our first decision variable, x1, is the number of elevators to implement in the new mega mall, and x2 is the number of escalators to implement in the new mega mall. Our objective coefficients, c1 is the unit cost of implementing an elevator, which we have discussed earlier, and c2 is the unit cost of implementing an escalator. And hence, the objective function for the primal formulation is a minimization function, and it equals $110.4 thousand times x1 plus $171.5 thousand times x2. Our objective formulation is subjected to a few constraints. The first constraint is based off the Company 1 minimum order. It states that the combined implementation of escalators and elevators has to be greater than or equal to 10. And for Company 2, the combined order of escalators and elevators has to be greater than or equal to 15. The third constraint is based off the Company 2 minimum order, where the number of escalators implemented has to be greater than or equal to 2. And of course, we have the non-negativity constraint because we can't have a negative number of escalators and elevators implemented, can we? Now let's look at how to find the graphical solution for the problem. First of all, we plot the objective function by choosing an arbitrary z-value. Now here we've chosen 700, and hence this black line that you see here is the plot for the objective function. Note that we are only paying attention to the first quadrant due to the non-negativity constraint, so we don't pay attention to these negative points. And now the first constraint for Company 1, as you can see in green, is outlined here. The second constraint for Company 2 is outlined in the blue. And last but not least, we have the x2 is greater than or equal to 2 constraint. Note that y is the same value as x2 in this graphing software. Now, to be able to determine the optimal values for x1 and x2, let's see if we can move the z function closer towards the 2 constraints. I'm going to pick a arbitrarily larger number, let's say 1400. And we can see here, if we get closer, that it indeed crosses the intersection of the 2 constraints, and according to this graph, the optimal values for x1 and x2 are both 5. Now, to solve the algebraic solution, for step 1, we have to rearrange the equation for constraint 1 to x1 equals 10 minus x2. The next step, we substitute the newly arranged equation into the x1 value of constraint 2. And as you can see, we have 10 minus x2 plus 2x2 equals 15, which then leads to the optimal value of x2 becoming 5. And finally, for step 3, we can choose to substitute the value of x2 back into any one of the equations, and if we substitute it back into the equation for constraint 1, we can see that the optimal value for x1 is also 5. Now that we've found both our graphical and algebraic solution for the optimal values of x1 and x2, we can plug them back into the minimization function for the primal formulation to calculate the minimum cost. Now, as you can see, we've replaced the values of x1 and x2 with 5s, as those are the optimal solutions. And finally, after we do the math, our minimized cost is $1,409,500. Now we have to present our ideas to our client. After all our calculations, we recommend that the wealthy investor should implement 5 elevators and 5 escalators in his mall. By doing so, he would minimize his total cost of implementation to only $1,409,500. Thank you. You can pay us now.
To solve the dual solution, objective functions and constraints are done opposite to what was done in the primal, such as changing equalities from greater than to less than, and the z function from minimum to maximum. In addition to that, changing decision variables from x to y's, and also switch the right-hand side's constraints of the primal to objective coefficients in the dual, and vice versa. To solve the left-hand side dual constraints, we take the transpose of the left-hand side coefficients and replace the x's with y's. As you can see, the z was switched from minimum to maximum, and the coefficients were replaced by the constraints, and y1 and y2 were previously x1 and x2. And as you can see in this slide, the constraints for the dual formulation and the non-negativity constraints. Notice that we ignored the third constraint, which is x2 is greater than 2, because it's a non-binding constraint, which means that it won't affect the objective solution.
Now, let's find the graphical solution for the dual formulation. Up here, we see the equation for the optimal function, where we have chosen an arbitrary z value as 30, and once the line is plotted, we can see here that it is this black line. And of course, we're only considering the first quadrant due to the non-negativity constraint. Below that, we see the first constraint highlighted by the blue line, and the other constraint highlighted by the red line. Now again, like the primal, to confirm that the intersection of the two constraints is indeed the optimal solution, I'm going to choose an arbitrarily large number as z to move the z function line closer to the intersection of the constraints. So I choose 1400, and we can see that the line passes through the intersection of the constraints, and hence the optimal solution of the dual formulation is y1 equals 49.3 and y2 equals 61.1. To solve the algebraic solution for the dual formulation, we use the exact same process that we used for the primal. First, we rearrange one of the constraint equations. If we rearrange the equation for constraint 1 from y1 plus y2 equals 110.4 to y1 equals 110.4 minus y2, and then in step 2 replace that as the value for y2 in the equation for constraint 2, we can see that we have a solution, an optimal solution of y2 of 61.1, and all we have to do now is plug that back into, let's say, the first equation, and we'll have y1 plus 61.1 equals 110.4. Hence, the optimal solution for y1 will be 49.3. Now that we have the optimal values of y1 and y2, we can go back to the original objective function and plug that back in to find the maximized solution. Now, when we replace y1 with 49.3 and y2 with 61.1 in the objective function, the result that we yield is 1,409,500. As you can see, this is the exact same objective solution as the primal formulation, which means that our calculations are correct.
Now that we've discovered an optimal solution, let's analyze some possible changes that could occur which may possibly change our optimal solution. This is called sensitivity analysis. And in order to carry out the sensitivity analysis, let's look at this sensitivity table provided by Excel. Here you will notice that the constraints and variables listed are accompanied by their allowable increase and decrease numbers. These values are used to determine whether a possible change in the formulation will affect the final values of the optimal solution. For this problem, we'll need the allowable decrease and increase values along with their respective shadow prices. Now let's make some changes to the right-hand constraints. Let's see what happens if we increase the minimum order for company 1 from 10 to 12 and also decrease the minimum order for company 2 from 15 to 13. Now, in order to correctly determine if the changes applied will not affect the optimal values of x1 and x2, we must first use the 100% rule. Here we take the absolute value of 12 minus 10 divided by the allowable increase, multiplying by 100%, we get 40%. Continuing on, we take 13 minus 15 divided by the allowable decrease, multiplying by 100%, we also get 40. Adding the 2% changes will give us 80%, which is less than 100%, allowing us to continue our calculation. Hence, increasing constraint 1 by 2 and decreasing constraint 2 by 2, we take our original value of 1,409.5 added to 2 times the shadow price of 49.3 and 2 times the shadow price of 61.1, we arrive at a new optimal value of 1,385.9. That is also in thousands, which totals up to $1,385,900. Similarly, let's make some changes to our coefficients. Let's increase C1 from 110.4 to 130.4 and decrease our C2 from 171.5 to 140. Looking back at our sensitivity table, for this problem we will need the allowable increase and decrease values for our coefficients. Now, considering the previous problem with the optimal solution of 1,409.5, let's use the 100% rule once again to determine our increase and decrease percentages, which will help us continue on. As you can see, our total changes end up being 68%, which is less than 100%, giving us the go-ahead to continue on with our calculation. Using our new changed coefficients, let's go ahead and calculate our new z-value, which totals up to be 1,352,000. Now notice that our optimal values of x1 and x2 remain the same.
And finally, we have our list of references. Thank you for watching.